video looks at vector representation in 3 dimensions and manipulating vectors in 3 dimensions, so adding, subtracting, multiplying. So firstly, the vector between 2 points in 3 dimensions, no different to when we were doing it in 2 dimensions. So the vector AB, which you can see by the pink line, we'd have to start at A, go to O, O to B, and then AB would be our resultant. So that would be AO plus OB, which is the negative of OA plus OB, which is minus vector A plus vector B, which you could represent as B minus A. So remembering from when we did two-dimensional vectors, AB, it's the second point, B minus the first point. So if we had AC, that would be C minus A. If we had DA, that would be D minus A. But you can always work them out and not have to remember that. So algebraic operations with 3D vectors in component form. So similarly to our two-dimensional vectors, we just add the corresponding values. So for the first one, we are going to work out A plus B. So A plus B is equal to vector A, which would be x1I plus y1j plus z1k. So that's using our A coordinate, and our B coordinate is x2i plus y2j plus z2k. So all we do is add the corresponding values. So it becomes x1 plus x2i plus y1 plus y2j plus z1 plus z2k. When subtracting, same deal. A minus B is going to be x1i plus y1j plus z1k minus, remember to put the brackets, x2i plus y2j plus z2k. And again, looking at corresponding values, and we will subtract them. So x1 minus x2i plus y1 minus y2j plus z1 minus z2k. Scalar multiplication. Now, if I'm multiplying by scalar lambda, then it's that minus the whole vector, and we just multiply each value by that lambda. So again, no different to what we did in two-dimensional. Now, parallel vectors. Two vectors can be defined as parallel if one is a scalar multiple of the other. So B would be parallel to A if B equals lambda A, some scalar times A. So watch the next video to see some examples.